So good morning everyone, welcome to Turbulence. We are continuing the chapter on scales of turbulent motion. In the last lecture, we discussed the idea that eddies form at the largest length, velocity and time scales, represented by this diagram, and then these eddies will break down via the energy cascade to smaller length, velocity, and time scales. And then this breakdown continues until the fluctuations are dissipated by viscosity. So we talked about this process. We reserve the subscript 0 to designate largest scales of fluctuations. We said at every stage of breaking down of eddies, you can calculate the Reynolds number given as the velocity scale of the eddies of interest, the length scales of the eddies of interest, and the viscosity of the fluid. So every stage has its own Reynolds number. And at the very end of this energy cascade process, the Reynolds number is so small that viscous dissipation is the dominating physics. So at the end of this, Reynolds number should approach 1. Then we started talking about Kolmogorov hypotheses that enable us to formulate and solve problems considering the energy cascade. And Kolmogorov was a mathematician, a Russian mathematician, who came up with the hypothesis and developed the mathematics of solving turbulence problems. So let's read the hypotheses. We discussed Kolmogorov's hypothesis of local isotropy, stating that at sufficiently high Reynolds number, the small scale turbulent motions are statistically isotropic. So the biggest motions are not isotropic. If you coordinate the reference frame, you're going to calculate different components of Reynolds stress, for example. But at a smaller scales, if the fluctuations are smaller than the largest eddies, then at higher Reynolds number, the turbulence is statistically isotropic. If you rotate the coordinate system, you get the same components of the Reynolds stress. Now let me introduce to you the Kolmogorov's first similarity hypothesis, which states as follows. It says that in every turbulent flow at sufficiently high Reynolds number, the statistics of the small scale for eddies less than a given size have a universal form that is uniquely determined by kinematic viscosity and dissipation rate. Okay, so if eddies are very small, the physics of turbulence can all be described by two numbers, or two quantities, kinematic viscosity nu and dissipation rate. Note that the condition for this to happen is eddies must be smaller than some range LEI, and we'll tell you what this LEI is. This length scale is known as the universal equilibrium range. Okay? So this is sort of a cutoff range. If eddies are smaller than this size, they're in the universal equilibrium range. If eddies are larger than this cutoff length, we call this range the energy containing range. It's a cutoff length scale. I'll show you pictures in a moment. But let's be satisfied with what we have here so far. So in this range, small eddies quickly adapt to maintain a dynamic equilibrium with the transfer rate imposed by the larger eddies. So in this range, small eddies adapt to maintain a dynamic equilibrium with the energy transfer rate imposed by the larger eddies. If you remember, the energy transfer rate was the rate of breaking the energy down to the next level of the energy cascade. Okay? So there is some sort of equilibrium that's maintained in this range. Given kinematic viscosity and dissipation rate, there are unique length, velocity, and time scales that can be formed. These are known as Kolmogorov scales. So if you know, well, we told you already that using two parameters you can define all the scales of fluctuations, and those two parameters with kinematic viscosity and dissipation rate. The three scales of interest would be length, velocity, time. Length, velocity, time, and we know them as Kolmogorov scales, and they can be defined in this way. These scales are the smallest scale of fluctuation. So this is the last stage of the cascade. And after this stage, you go back to viscous dissipation. So it's the smallest fluctuations you may get. The very smallest and dissipated eddies that do not break up into smaller eddies. And by definition, this should happen when the Reynolds number at the last stage of the energy cascade should be around 1. Okay? By definition, this will happen, and you can plug these two length and velocity scales in the Reynolds number, and you can confirm that they are in fact, the Reynolds number becomes 1. And it's not hard to see if you put in Kolmogorov length scale, eta, and Kolmogorov velocity, u eta, into this equation. You get nu divided by nu. So the Reynolds number would actually be 1. Okay. Also, the dissipation rate can be given by this expression, again uniquely described by kinematic viscosity, velocity scale of Kolmogorov scale, velocity scale of motion, and Kolmogorov length scales. Again, remember, this is the last scale before fluctuations turn into ordered flow, right? So this is the last stage of the energy cascade. These very small eddies have velocities in the order of u tau, have length in the order of eta, and they on average last for about tau eta. That's tau eta is the time constant, time scale for these smallest fluctuations. So this is the very last step, viscous dissipation. And also, if you remember, we said something about dissipation rate physically be the rate of transfer of energy. So its units must be energy per time, because it's the rate of breakup of energies, turbulence kinetic energy, into the next stage of the cascade. So the units must be meters squared per second cubed. And it is. You can verify. So units is meter squared per second cubed. Remember, for our purposes, there's no mass in energy, because we talked about energy per unit mass, right? Kinetic energy is m1/2 mv squared. From dynamics, we don't worry about the m part. We just worry about the v squared part. right? So V squared is meters squared per second squared, divided by another time, meters squared per second cubed. On the smallest scales, in high Reynolds number turbulent flows, turbulent fields are statistically similar. That is, they are statistically identical when they are scaled by the Kolmogorov scales. So that one is another profound statement, which means that down after some given cutoff length scale, the turbulent motions are statistically similar or self-similar. Think about what we said about the triangles, the similarity in a tree. Phenomena in physics are similar if they are similar to a subdomain of themselves. And we made the example of the trunk of a tree and the higher branches. They all exhibit the same angle on average, statistically speaking. Same thing about turbulent past the cutoff length scale. So if you zoom in a stage of energy cascade, you see similar phenomena but happening at different scales. Maybe velocities get faster, maybe length scales get smaller, maybe time constants change. But they are similar at every stage of the cascade. So this is how we show the similarity. In other words, the ratio of the smallest to largest scales are given by only the Reynolds number of the flow. Okay? Kolmogorov length scale divided by the largest scales of fluctuation is Reynolds number to the power of -3/4. Kolmogorov velocity scales by the largest eddies velocity scale is scales with Reynolds to the power of -1/4. The time constant for the Kolmogorov eddies and time constant for the largest eddies scales with Reynolds to the power of -1/2. And these are really, really powerful scaling relationships, because you can start with a very complex flow and develop a simple model to model it. Whoever designs and develops turbulence models uses these scaling relationships. So, and I can put it in different words, that these relationships are extremely powerful, because without having to even measure or simulate turbulent flow, it's possible to infer the Kolmogorov scales and understand what length, velocity, and time scales they are with respect to the largest eddies. I don't even need to do any modeling or advanced calculation. I just know. The Kolmogorov scales using the Kolmogorov hypothesis. I'll show you a nice picture in a moment. But before I show you the picture, I'll tell you the... Actually, let me show you the picture. I can explain half of it, right? And then I tell you the Kolmogorov second similarity hypothesis, and then I explain the rest of it to you. So we told you eddies form at the largest scale, L0. So that's the largest type of eddy you can get. This big L is length scale of the problem. I mean, this could be the size of a building or diameter of a pipe around which turbulent flow is occurring. So that's fancy capital L. Then the largest eddies that form in the system are very close to the length scale of the problem. We know them by L sub naught. So it's that eddy. Then this is the cutoff eddy length scale, EI, LEI. And then after this, the equilibrium universal range begins. So all what we said about self-similarity of the cascades of energy motion, we're talking about this range. Okay? And we told you that only viscosity and dissipation rate are sufficient to describe all the dynamics of motion in this range. You only need two parameters to describe those. Let me tell you the second similarity hypothesis that Kolmogorov proposed, and then I will tell you the rest of the story on that picture. The Kolmogorov second similarity hypothesis says that in every turbulent flow at sufficiently high Reynolds number, the statistics of the motions of scale L in another range that's not very close to Kolmogorov, in fact that's far away from Kolmogorov, bigger than the Kolmogorov length scale, and is really far away from the energy containing length scale. It's actually in between, it's far away from either ends of the spectrum, have a universal form that is only uniquely described by epsilon, or dissipation rate. You don't even need viscosity for that range, kinematic viscosity. Everything can be, the whole story can be told by epsilon, or dissipation range. Okay? Which means that if I only look at the mid-range here, epsilon is all I need. If you want, in other words, this range can be uniquely described by dissipation range. You don't even need to know what the viscosity is doing, because viscosity is not acting as a dominant physics in this range. It is just break by inertia. It's only the very smallest scale that then both viscosity and dissipation range kick in, or dominate the physics of energy cascade. Okay? So this middle range, where eddies are much smaller than the energy containing and Kolmogorov length scales, this is known as inertial subrange. It's a very well-behaved, convenient range of turbulent motion that we know very well how to deal with using empirical correlations or calculations. So let me read the remaining of the paragraph. This hypothesis builds on the previous hypothesis in a way that length scale of the fluctuations is significantly larger than Kolmogorov length scale eta. Then only inertial effects are dominant, as I said, and the viscous effects should not determine the statistics of turbulent motions. For this hypothesis, it is useful to define another length scale, let's call it LDI, which is the cutoff range, LDI, which is the cutoff range for inertial subrange and dissipation range. We can then specify a range in between these two cutoff ranges as inertial subrange. Okay? It's all about scales, right? For a flow, I mean, let me put it this way. Let's say the building may be 50 meters, the size of this building. Okay? The largest eddies formed around this building are in the order of 50 meters, maybe 40 meters, right? Maybe 45 meters, maybe 60 meters. It's the same range. The cutoff range there may be for the building 20 meters, right? Then from 20 meters all the way to, let's say, I don't know, 5 centimeters, in that range, all the fluctuations are described by dissipation range. That's the dissipation rate, that's the inertial subrange. And then after 5 centimeters all the way down to a millimeter, for example, is the dissipation range. So turbulent motion fits in nicely within these length scales. Of course, I could draw the same diagram for velocities or the same diagrams for time scale, tau, right? Of course, I mean, velocities could go up or down, or time constants may be very large here and small here. So we know the physical world in space and time, right? Or the combination of two, this is velocity. So you can sort of come up with these scales and describe the physical phenomena. Sounds like relativity, by the way. I mean, if you wonder, people who study turbulent motion sometimes end up in quantum mechanics and relativity. I mean, fluid dynamics, right? Because it's all about motion. Scales of motion, velocity, time, and length. And that happens. Like if you know Werner Heisenberg, the grandfather of, one of the grandfathers of quantum mechanics, has proposed the uncertainty principle. His PhD thesis was on turbulent flow. Right? So we are talking about deep physics here, at a very fundamental level. So really fun. Energy cascade. Anyway, we're showing you the energy cascade here using the length scale. So it should be familiar to you. So that closes the discussion on these scales. Now for the inertial subrange, having L and epsilon, it's possible to estimate characteristic velocity and time scales for an eddy. Now, when you talk about the middle range, then things are very convenient. Then these velocity, scale of fluctuation, and eddy length, remember, it should only depend on epsilon. Viscosity should not be here. So uniquely described by epsilon. And time scale of fluctuations, again, uniquely is described by epsilon, dissipation range. Of course, L needs to be there because you have to tell me what length you want to look at, right? So really, only uniquely is described as a function of epsilon, dissipation rate. Really profound. And let me again reiterate that for a statistically stationary flow and in the inertial subrange, the rate of energy transfer tau from eddies larger than L to eddies smaller than L is approximately the same as the dissipation rate. I mean, we told you there is equilibrium in the inertial subrange. So the rate at which kinetic energy transfers to the next stage, right, kinetic energy L, divided by the time those scale of fluctuations last, must mean the rate of breaking the energy down to the next level. This is the very definition for epsilon, dissipation rate, or the energy transfer rate. So these are related in the inertial subrange. Any questions? Very deep. This is my most favorite chapter here in this course, by the way. We owe it all to this chapter that we can solve real and practical turbulence problems out there in the world. So thanks to Richardson and Kolmogorov. The energy spectrum. Turbulent kinetic energy in a flow is distributed among different eddies with different length scales. So the game is all about the game of scales. So fluctuations come and go in different scales. That's why we need to develop some sort of a distribution that can quantify these scales of motion. We know this as energy spectrum function, E as a function of kappa, and we would like to describe size of fluctuation using wave number. So kappa is wave number of the flow, 2 pi over L, and L is the size of the fluctuation. Then the nice property of the energy spectrum function is that if you integrate it between any two limits, let's say kappa A or to kappa B, or a range of wave numbers or fluctuations, this gives you exactly the turbulence kinetic energy associated with that range of wave numbers. Okay, we showed you this in a previous chapter, so I'm not going to dwell too long on it. Likewise, the dissipation rate can be analyzed for a range of wave numbers using a different type of integral. The energy spectrum is here still also, but then there's a multiplier to the energy spectrum for the inertial subrange. And if you take the integral of this expression, you get the dissipation rate. Remember, this is only true for the inertial subrange. Don't use this for energy containing range or the other range, which was known as dissipation range. Only for the inertial subrange. And for homogeneous turbulence and in the inertial subrange, remember, well, if your ranges were LEI, LDI, there is a corresponding range for the wave number, right? It's the same as saying if you want L be between LEI and LDI, that's equivalent to saying kappa is less than kappa DI and kappa EI, right? The limits swap because wave number has an inverse relationship with L. So that should not surprise you. And people have fitted the energy spectrum with well-defined functions. One example is this, where the energy spectrum in the inertial subrange has a power of 2/3 relationship with dissipation and rate and -5/3 power relationship with wave number. This is also known as the Kolmogorov -5/3 spectrum. Okay, and if you want, I can show you pictorially. Well, it means that if you plotted energy spectrum, which is E kappa versus the ln or log of kappa, you get some shape. Only in the inertial subrange, the slope of that line will be -5/3. -5/3 is the slope of that line. And if you want, you could show kappa DI and kappa EI in this plot. So only in the inertial subrange that's the slope you get. And remember, this is only used for momentum. It's a U component of velocity. If you look at other complicated statistics, let's say temperature fluctuations, could be different. I mean, in fact, the whole shape of the energy spectrum function can be different for different velocities. And in our group, we do it for all kinds of turbulence quantities. We fit these shapes for heat flux, turbulent heat flux, Reynolds stresses, the normal components, the shear components, scalar fluxes. You can fit these energy spectra for any turbulence statistics of interest. It's a very broad topic, and people do it all the time. Any questions? The next topic is two-point correlation. This is somewhat new. All these statistics we showed you so far were measured in one location, but at different times. Like if you remember, our correlation was measured in one location, but a time shift or a delay in the measurement. But we also told you it's possible to make measurement in two locations and calculate a correlation between the two measurements. And that's what we're going to do here. Here, we redefine autocorrelation function as a 2-point and 1-time statistics. And let me begin with an example. Okay, let's say I'm interested in the correlation of u component of velocity here and u component of velocity here. I'm interested in these 2 points. So I put one anemometer here and I put another anemometer here. I conduct an experiment, like the ping pong experiment. I measure at some given time, let's say at 11:15 for today. Exactly at that time, I measure two fluctuations here, both in u. suppose I could repeat the same day. I come back again, exactly 10:45, measure those two components. So I have now two pairs of numbers. Come back again, the day repeats itself. It never does in reality, but let's say it did. Then I again measure those two fluctuations. So if I repeat this indefinitely, then I can calculate a sort of an ideal mean for these correlation of these two fluctuations. Of course, in practice, pure ensemble averaging is impossible unless you're doing modeling, because you can repeat an experiment in the modeling world. But yeah, I mean, you would do time averaging in practice. So you could do that, and you could look at the correlation between any two fluctuations of interest. I could look at U here and U here, maybe U here and V here, U here and W here, or W here and V here. I could combine any two pairs of components. But what do I have X? Well, it depends on where I am. Let's say I could measure these 2 points. X for the first point is from the origin. So the origin is here. That's X. But I could do the measurement here. But the position of the first point with respect to origin changed. So X could change. I could do the 2 here. I could do the 2 here, right? These two can be positioned anywhere in space relative to one another. Of course, the distance between them, the position vector between them, you can think of as vector R. R goes from point 1 to point 2. That's vector R. So you see R, I need two pieces of information, where I am at, X, and then R, which is the relative position of the 2 points of interest. Of course, I have time here too, because not all flows are statistically stationary. You could get transient flows, so you might, say if the day repeats, you might do this at any second of the day, if you're interested, for infinite number of days. So as you see, the 2-point and one-time statistic takes a lot more arguments than the autocorrelation. So it can be a little more demanding. Why do we calculate this autocorrelation? Because it tells us important information about the size and length scale of eddies. To say anything about the size of eddies, you must measure different locations in flow. If such a correlation sharply decreases with the increasing distance between the 2 points, the turbulent flow ought to exhibit small turbulent eddies. On the other hand, if this correlation is significant, even larger distances between the 2 points, then the flow exhibits large turbulent eddies. Suppose I have 2 sensors here. A very small eddy comes here, goes past the first sensor, and then goes past the second sensor. It's very small. It cannot influence both measurements simultaneously. I'm not going to see any correlation. Let's say now a very huge eddy came. Right? It was so big that by the time it reached point 1, it also influenced point 2. If a very huge eddy swept across these 2 points, then I would measure some correlation. That's why you need 2-point measurement to say something useful about the size of eddies. It's a very important concept. Although you can make some simplifications for homogeneous and isotropic turbulence, you know, the dependence of X can be removed. It's homogeneous. It's every way turbulence is the same. I can remove X from this in homogeneous form. Isotropic also, that I can remove the directional dependency, right? Regardless of their orientation. So really, I can knock X out of the 2-point correlation. And further, I can knock the vector aspect of R, so I can look at the scalar distance between the 2 points. If my flow is isotropic, so it becomes very simple. Further, it's convenient to express components of the autocorrelation function after the rotation of the Cartesian coordinate system, such that one of those axes is aligned with vector R, which means that flow must be isotropic, right? Let's say this is x, y, z axis, like x, y, z, okay? One point is here, another point is here. Now, if flow is isotropic, I can rotate my coordinate system. I rotate it, so one of those components point directly from point 1 to point 2, or along R. See what happened? So I rotated this coordinate system, so one of those axes, let's say the primary axis, E1 or X, points from 1 to 2 or in the direction of R. This can further simplify my work. Remember, only for isotropic turbulence, not always. So that the other two axes, let's say axis E2 and E3, then become normal, perpendicular to the R. Right? E1, let's say E1 was X, is along R, point 1, point 2. Then E2, E3, or Y and the Z axis are now normal to R. After you do this rotation, then you can calculate some very physically meaningful two-point correlations, and we know them as the components of the autocorrelation function. R11 is the component along R. Let's say X as it was the first component. We know this as the longitudinal autocorrelation, or R11 same as RLL, because L is for longitudinal. And the normal components to R we know as 2,2 or 3,3 as the normal or transverse autocorrelation function. This little n is put here to designate normal. If flow is isotropic, the normal or transverse components of the autocorrelation should be the same. R22 and R33 are the same, but there's no reason why the longitudinal should be same as the transverse autocorrelation. That's important. I'll show you a picture briefly. Okay, look at this picture. I mean, this could be X, Y, Z, right? E1 is the first component which I would like to align with position vector R, right? So if E1 or the x-axis is along the position vector between the 2 points, then the first component of momentum fluctuation, U1, or this could be U, is along that R. So if I calculate the autocorrelation function, I'm calculating RLL. But the other two components are normal. Let's say Y, or the V component, U2, the second components of fluctuations are normal to R. So this is R22. It's a transverse normal component. Likewise, if I look at the Z direction, or W, or U3 component of momentum, again, they are normal to this vector, so I calculate R33. For isotropic turbulence, these should be the same. It should be the same, and they should be different from RLL. Okay? So far, so good? You might be thinking, what the heck are we doing? When am I ever going to need this? You need it. If you do some really good fluid analysis, all of these come up. I can tell you, I do atmospheric work, ventilation, building ventilation, airflow, in different domains. These things come up all the time. If you want to understand what the model is doing, open foam or fluid or CFX, what wall functions are doing, these will come up. So let's enjoy them while we can. It was stated earlier, so let me now say you something about normalizing these autocorrelation functions. It was stated earlier that if the separation distance between the 2 points is 0, then you're actually calculating a component of Reynolds stress, right? Okay, if the 2 points are the same, the distance is very small, the 2 points are the same, then I look at two different directions of fluctuations at the same point, and I repeat the experiment, like U and U. Repeat the experiment. U and U. Repeat the experiment. I'm calculating the normal component of Reynolds stress, right? So if the 2 points are collapsed and merged into 1 point, then I'm calculating the same simple 1 point statistics I was talking about, which was Reynolds stress. Okay, so if the separation distance is 0, you're actually calculating a component of Reynolds stress. And depending on what U, I, and J are, you may be computing U squared or U12, U22, U32. You may be even computing the Reynolds stress, like UV, UW, VW, or U1, U2, U2, U1, U1, U3, and so on. If it's isotropic condition, if I and J are the same, all of them are the same, like U squared, V squared, W squared, they're all the same. Or U1 squared, U2 squared, U3 squared, all the same. Then the other correlation function can be expressed in a general form as follows. Okay? Somehow I'm saying that I can factor out a component of Reynolds stress out of the longitudinal autocorrelation, and then this is some way of normalizing that. If you like, another way of saying this is this: F RT is the longitudinal component of autocorrelation divided by that. Okay, just some sort of a normalization. Likewise, the transverse component can be normalized. If you factor out a normal component of Reynolds stress, U squared, then you're left with G. Remember, F and G are mainly functions of separation distance, R. But of course, for non-statistically stationary flow, they can also be a function of time when you're making the measurement for transient flows and so on. By definition, if there is no separation distance, both F and G must be equal to 1. And they vary, actually decline, as the separation distance increases. So this plot is full of stories. Well, if I increase the distance between the 2 points indefinitely, eventually there should not be any autocorrelation. If I put one anemometer here in Guelph and another anemometer in Toronto, I'm not going to see any correlation. But if I put them very close to each other, they're going to be 100% correlated. Okay? So these must be starting at 1. That's the first nice thing. You can see another thing, which curve is higher than the other. F is higher than G, which means that on the longitudinal direction, you can expect more correlation. For the component of fluctuation that's along the position vector R between the 2 points, you can expect more correlation. Okay? And finally, G can become a slight negative at large separation. That's kind of bizarre, but it's true. Okay. And again, even this comes up all the time. When you design turbulence models and you want to formulate, close your system of equations, you may need to make some assumptions about the size of eddies. If you want to make some assumptions about the size of eddies, these functions come up and you have to know them and make approximation and do something mean, you can imagine this may be approximated as an exponential decay, for example, or a negatively sloped line. It's very extremely practical. And in fact, now I want to tie it. Now is the perfect time to tie this to the size of eddies. Okay. It's possible to calculate now new integral scales, integral length scales. If the autocorrelation function is known, now we can calculate integral length scales. Now this is parallel with the integral time scales, which we calculated in a few chapters back. The first length scale is the longitudinal integral length scale, which is obtained by integrating this function f over all possible values of r from 0 to infinity. If you remember, we did this for time scale. We integrated autocorrelation function tau, or rho, I apologize, rho, and it gave us integral time scale. And likewise, you can calculate the transverse integral length scale by integrating function g, okay, which is characteristic smaller than these. If you want, you can actually average the two length scales to come up with one length scale for the turbulent fluctuations. And I can show you an example. Let's say you have flow near a wall. So here's a wall. There's flow near a wall. Flow near a wall. X. Say X. You have X. You have Y. You have Z. Let's say Z is normal to the wall. And then you put two anemometers and measure these functions f and g. You want to characterize, I mean, of course, a lot of eddies would form, right, of all different sizes. I mean, there could be many eddies, but statistically speaking, you can describe all of these eddies with one longitudinal size, if you want, like LXX or L11, if you want. You can characterize all of these eddies by two transverse sizes. One would be LZZ, which is a component of LNN, and there would be another one, LYY, which is also another component of transverse. So statistically speaking, you get like oval shape or like eggs, like elongated eggs. As you think of eddies as elongated, because we told you L11 should be larger than L22 or L33. Okay, so yeah, it's maybe L. Statistically speaking, that's the shape of your eddies. Okay, any questions? Sounds good. The structure functions. Again, extremely useful and practical for model development. And we are in good shape. The second order velocity structure functions are useful statistics to describe the nature of turbulent flows, particularly the dissipation rate. And as we said, dissipation rate is a big deal. You must be able to quantify what dissipation rate is, and that's how you can solve engineering problems. And dissipation rate, if you remember, solely describes nature of fluctuations in the inertial subrange, and it's along with kinematic viscosity, it describes nature of fluctuations in the dissipation rate. So it's big deal. You must be able to characterize it. The structure functions will help you do that. The second order velocity structure function is another statistic we calculate, which is the covariance of the difference in velocity between 2 points, x and x plus r. So think of the same two sensors that we had. The one sensor was here, sensor number 1, sensor number 2. The number 1 was positioned at x with respect to the origin, and then the distance between 1 and 2 was r. Okay? To calculate a structure function, be careful, I'm not talking about fluctuations anymore. I don't have a small u. I have capital U, which means that I'm talking about the difference between total velocity in the I direction between the 2 points, and then the J directions between the 2 points. I can calculate some sort of correlation with that. Let's say U, not fluctuation, total velocity here in the x direction, U, or U1, and then U1, the difference of the two, then multiplied by V components, like V, and then who knows V, and then the difference of the two. I can calculate some sort of a covariance there. This is known as the structure function, and again, it's a function of displacement displacement vector r and x and t time. Extremely useful. It is understood that the structure function is computed as an ensemble average for a given location x and the separation distance r. And a particular time, of course, if the flow is non-statistically stationary, it seems that only eddies of size r or smaller can make a significant contribution to the structure function, and that's true. Larger eddies, you're actually not going to be able to see or detect. So if you have two sensors here, they are able to see eddies as big as the separation distance between the two. If there's something that's much bigger, like 100 meters, and large eddy that sweeps across the two sensors, you're not going to be able to detect those eddies. Okay? And that's extremely important. I can show you a picture for that also. It's going to be very similar to what I showed you for interlength scales or other covariance. So here you have, instead of r, you have d, which is for structure functions. And again, it could be defined for longitudinal direction, where you look at the component of velocity along vector r, or u1 along r, or the transverse components of velocity, u2 and u3, with respect to r. Of course, I have rotated my coordinate system, so I get E1 or x aligned with r. Okay. And we can make some simplifications. In homogeneous turbulence, the velocity fluctuations are independent of location. So the structure function does not depend on location x. Okay, so again, homogeneous turbulence should be the same everywhere. Shouldn't matter where I position the two sensors. Here, 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 here. Also using Kolmogorov hypothesis of local isotropy, if its eddies are small, too small, or if R is significantly less than energy containing range, then I can remove capital R and replace it with lowercase r. Okay? And I can freely rotate my coordinate system. So E1 is along R, and then I can report the longitudinal or transverse components for structure functions. So D1 var or DLL is longitudinal, D22, D33, DNN is transverse component of structure function. Again, the transverse ones should be the same. So D22 and T33 should be the same. And the underlying longitudinal is D1 or DL. Transverse is D2233 or NN. And now I fully justify even defining this in the first place. It has been found that structure function is directly correlated with dissipation range. So if you measure it in a flow, you're actually measuring dissipation range. And that's how useful it is. Dissipation rate. Again, for isotropic turbulence, I can replace vector R by scalar R given the first Kolmogorov hypothesis, R less than fancy L, then D can be neatly described by kinetic viscosity and dissipation rate, the universal equilibrium range. And in the middle range, in the inertial subrange, only epsilon or dissipation rate is related to structure function. And in fact, the relationship is structure function is related to dissipation rate to the power of 2/3. Again, R here is somewhat known because you know the distance between the two sensors. You can calculate it maybe for a small distance, for a large distance. If the R is in the same range as the length scale of inertial subrange, you should be able to fit a very nice curve and calculate dissipation rate from the fit. Okay. So now the longitudinal. And then I have the transverse also. So this constant C2 has been fitted empirically to be around 2, and you can notice that the transverse direction is different from the longitudinal direction because there's a different coefficient here. So, any questions so far? The next piece is very important, and I have 10 minutes. I can very nicely dedicate this time to it. Is the Taylor hypothesis. So Taylor was a very famous British scientist who contributed massively to the field of turbulent flows. He was, in fact, he lived around the same time as Richardson and Prandtl did. So he was the counterpart of Prandtl. And he realized that it's extremely difficult to do any useful measurement in turbulent flow because you need a lot of sensors and you have to put them in so many different spatial configurations. It's almost practically impossible to measure anything in turbulent flow in the pure sense or in the perfectionist sense, right? But he said, look, I can do a better job. Maybe with one sensor I can measure a lot of useful statistics out of the flow. Well, why? Measurement of one-time and two-point correlations is extremely difficult because you need two probes and you need to place them in many different relative spatial distances. Practically impossible. And you need to have a large number of experiments. However, alternatively, you can move the probe. Probes are not stationary anymore. You get one probe, but then you move it through the flow really fast. Really fast. So, if the probe is moving with speed v along this direction, r, well, there is a simple relationship between speed, time shift, and r. And you can calculate a new form of autocorrelation function. And I know I put this as R sub ij, but put a superscript m in here, which means this is autocorrelation for a moving probe. And if the probe is moving at a velocity v, for any given time shift s, the probe has moved a distance r. Which means that by how fast I move this probe and delaying its measurement, I'm actually measuring two locations in the fluid separated by distance r. Okay, again, sounds like relativity, and it really is. So the observer is moving now, if you want, and at a very fast speed. If I'm moving really fast, I mean, I'm not saying the speed of light, so don't go too far, but let's say really fast. Then, if it's fast enough, the moving probe measures the same statistics given a time shift as two stationary probes would have with a relative distance r. So with one sensor, I did the job of two sensors. So that means a lot of research funding savings if you can't buy fancy equipment. And Taylor realized this, and he said that this can be put in very useful use for all kinds of measurements. And in fact, this principle is the bedrock of a lot of turbulence measurements. If you've heard of hot wire anemometers, the assumption there is the same, which means that you have a wire which you fly this really fast into a flow, and then this wire measures flow velocity at extremely high frequencies. I'm talking about kilohertz, if not megahertz. Then it can measure two-point correlation. If you fly an aircraft through the atmosphere, aircraft generally fly much faster than the wind. Okay? Then again, an aircraft can measure two-point correlations in the atmosphere if it flies fast enough. So this is a very important concept. Now, I will put a picture. I've got 5 minutes, but let me just close the text for this chapter. If you're in my line of work where you need to measure a lot of atmospheric flows, you could put a stationary probe in the atmosphere and then assume it's measuring the two-point correlation if certain criteria is met. Here V is the speed of wind. Okay, because probe stationary, now the wind is moving, background air is moving. Or anytime you have a stationary probe, it could be in a water channel or the Archimedes group, then the background water is moving. If it's moving, the background water is moving fast enough compared to the fluctuations, then you can assume Taylor hypothesis is valid. And in other words, eddies are frozen with respect to the stationary probe. That means an eddy that passes a probe doesn't change its shape. I'll put a picture to you. And then if this frozen eddy hypothesis or Taylor hypothesis can be used, then you can calculate dissipation rate, two-point correlations, and all the rest for your flow. And the condition is the fluctuations must be somewhat conveniently and conservatively less than the mean flow. Let's say in the atmosphere, fluctuations of wind divided by mean wind is 0.5 or less. So fluctuations are small compared to background mean motion. If that's the case, the Taylor hypothesis is a very good approximation. And you can use it for all kinds of flows, even in laboratory scale. In water channels, wind tunnels, all other situations. Now, I would show you the picture. What do we really mean by the Taylor hypothesis? I have 5 minutes and I can do that nicely for you. So Taylor hypothesis. Imagine eddies are frozen. In a fluid as they travel past a stationary sensor. Let's say I have a very simple bound layer flow. So X, Z, bound layer flow. So the flow is going to go down. Okay? And here's my sensor. It's an ultrasonic anemometer. It's sitting here. Let's say I want to make it fun. Let's say the eddy is in the shape of a horse. It's like a donkey. This is frozen, which means that this eddy comes. It's still the shape of a horse. It's not changing much. And it just keeps going down. Maybe realistically it's deformed a little bit. If you wait long enough, I mean, it could sort of deform a little bit. But by and large, it's still a horse. So frozen horse. With one sensor, I can measure all the turbulence, 2-point turbulence statistics, because the horse is the horse is the horse. So with one sensor, I can measure the same flow. With one sensor, I can measure the same statistics as if I would have had 2 sensors. Why am I saying this? Because, well, if I want to measure the nose and the tail simultaneously, I need 2 sensors. Well, these are the 2, and the 2 measures here and here, right? But if the eddy is frozen, I don't need 2 sensors, because I can measure the nose and then just wait until the tail goes past the sensor, right? So things are much, so can use Taylor hypothesis, and this will happen if fluctuations over mean flow are much less than 1. Say if this is around 0.2 or something like that, I can use a Taylor hypothesis and the horse is not going to change significantly. But not all flows exhibit that. I could have a horse which keeps deforming, and by the time it goes some distance down, maybe it becomes snake. Right? A lot of flows do that. The eddies are not frozen, they significantly change in shape. Then I cannot use the Taylor hypothesis, because now I need 2 sensors. Right? So in this case I cannot, so I'll say non-frozen horse. Frozen horse, if that's the case, then cannot use Taylor hypotheses. In other words, now fluctuations could be in the order of 1. They're no longer significantly less than 1. Okay? This is a very limiting condition. You cannot do much about these flows and say any much about the structure of the fluctuations or size of eddies. You need a lot more sensors. It's a very practical assumption that you can make with Taylor hypothesis. So that closes the chapter. I'll do a problem for you next time. Please do not fall behind on your computer assignments. I gave you a lot of freedom to complete them on your own, at your own pace, but they must be submitted by the deadline. So please quickly catch up with those and come see me in office hours or otherwise, so we can help you out with those. Okay, so this Thursday we're going to finish frequency domain. On Tuesday we solve sample problems for helping you for the upcoming term test, which is on the following Thursday. Sounds good? Great. Any questions? Fantastic. Okay, see you next time.